Welcome, this is lecture number 58. In this lecture, we are going to talk about overview of fixed and variable frequency digital control architecture. So, in this lecture, in fact, in this course the digital control is just an introductory part, but it could be a separate course altogether, but just to give some idea whatever we have learned, how can we go for digital control so that we can apply tuning and other stuff. So, in this lecture first I will talk about digital voltage mode fixed frequency voltage mode control, then I will talk about fixed frequency digital current mode control different techniques, then variable frequency digital current mode control and some event based sampling technique in variable frequency digital current mode control. So, in this we will start with analog voltage mode control, and we have already discussed in analog voltage mode control, that means what we have discussed, that we have like a reference voltage and we are trying to design a voltage regulator, and this is my actual output voltage and this is a sensor, and typically this could be a resistive divider, and then this sense voltage goes to our, this is the sense voltage here, and then error voltage, and then this is the output of the controller. And if we generally consider operational amplifier op amp for implementing this controller, but op amp also have a supply rail. So, we will come up, there will be a saturation limit here, and then we have discussed there is a pulse width modulator block. In fact, we can do for variable frequency control, then we will have either constant on time, constant off time modulator, or it can be hysteresis control, and then it goes to, in fixed frequency we have duty ratio, and that duty ratio goes to GVD, control to output transfer function, that we have already derived. And then this control to output transfer function output, that means it reflects the change in duty ratio, change in output voltage due to the change in duty ratio. This one is the audio susceptibility, which reflects the change in output voltage due to the change in input voltage, and the output impedance reflects the change in output voltage for the change in load current, and we need to take into account the sign, because if we are talking about a sinking current, then negative sign will come into picture. So, adding all together we are getting, this is the output voltage variation. Now, if we want to go for digital control, the first part that in our feedback loop we need to incorporate A to D converter. In fact, this sensor circuit, whatever we have considered H transfer function, it is still there. That means, we still need to consider resistive divider and unity gain buffer and some signal conditioning circuit, which should kind of try to match the impedance of this signal impedance of the output of this sensing circuit with the input impedance of the A to D converter. So, there has to be some matching criteria, and then this signal, so that the ADC should not be loaded, then A to D converter is used to convert the analog signal into digital signal, and this goes by three things. One thing is there is a sampler block, like a mathematical you can represent, then there should be a quantizer block, because the sampling block will sample the voltage or any signal that we pass at different discrete level, right. That means, we have to take the sample voltage at t equal to 0, t equal to some capital Ts, then twice Ts, and so on. If we talk about uniform sampling, after every fixed interval of time we will take a sample, but there can be non-uniform sampling also, that we are going to discuss, when the time period can also vary. Now, once we sample, then this sample signal has to go through, like in the ADC there is a finite number of bit, that means whether we are talking about 8 bit ADC, 9 bit ADC, 6 bit ADC, and we know about the resolution of the ADC. So, ADC will discretize in amplitude also, because quantize I will say, because it has a finite resolution, and depending upon the number of bits, we can define what is my quantization voltage level. But after this quantized voltage, then generally there has to be one codifier or coder, which convert what type of code you are getting, because it will be a stream of binary number, and that can be represented either in 2s complement or offset binary or straight binary. So, depending upon different architecture, but In general ADC we consider 2s complement. So, this kind of coding also need to be considered, because accordingly the output number, binary number which is coming out of the ADC will be treated whether it is a 2s or offset, because if you do not take into account this coder, then you may completely misinterpret the data with the real world analog signal. So, in this particular digital control we are talking about, there is a sampler and there is a quantization block, and we will see what is the impact of this sampling and quantization effect in this digitally controlled converter. Once we get the quantized voltage level, that actually compare with the reference signal. That means you can think of this whole block is like digital block. So, starting from this process, this whole block is digital. So, this is a number, this is a command, I will say it is a command, it is a reference command which is a number, and your output voltage will be compared, and the error voltage which is again the quantized discrete voltage or number, that will pass through a compensator, and generally it is a digital controller which can be PI, PID controller. There are variety of compensator that we can consider. You can talk about type 2, different type of compensator like lag lead compensator and so on. But the compensator voltage, if we talk about this, we call about control voltage, and in analog control it is typically compared to the sawtooth waveform. For example, if we talk about analog, PWM, analog PWM. So, in analog PWM we have a sawtooth waveform like this, and then we have like a control voltage like this. So, this is my control voltage in case of analog. Okay. Let us say, just to be specific, control voltage for analog. What will happen? The same thing for digital. If we want to draw something similar or equivalent, it will be like a staircase waveform. You may think the easiest one is the counter based approach, where there will be a kind of a staircase waveform, and again it will reset, it will go like this. So, in average sense, you can think of this slope is something similar to analog control. Okay? And interestingly, we will see that this control voltage, what is coming from digital, this will change, update according to the sampling and the computation rate, because it will only update when you get a new sampling data. That means the sampling data get updated, and that updated data will be added, and the control will also be updated. So, we need to remember that the clock used, if you say the clock, that means your computational clock, and if we talk about the sampling clock, so these two should be matched, they should be synchronized. But sometimes what happen, in some cases we may sample at a higher rate, but we may compute at a lower rate, because the ADC can be used sometime for kind of transient detection circuit, where we need to sample at a faster rate to identify when the transient happen, or in some cases we are just looking at the error voltage, whether it goes beyond or not. But in general, most of the cases the sampling rate of the A to D converter is same as the controller computation, because they will be sync the same rate. So, it is a uniform sampling rate. So, we are not talking about any multi-rate sampling here. So, that means now the next question you may ask, that will come to our mind, what should be the sampling rate? What should be our sampling rate? Should it be higher than switching frequency, lower than, same, what? If it is higher, in what factor it should be higher? Then we will also see what is the impact of sampling, like in terms of power spectrum, delay, stability, that also you have to see, and then what will be the impact of quantization resolution. So, in the next lecture, these two things like a delay and the quantization effect we will see, but in this lecture we are going to see architecture, where we want to see at least the power spectrum, because we need to take a decision what should be my sampling rate. Okay? And if we take a different sampling rate, then if I take the power spectrum of actual analog output voltage And if you take the power spectrum of the discretized or basically digitized voltage, how is it, how are they going to be whether they are going to be same or they are going to be different. So, we need to first understand the power spectrum. What is power spectrum? Suppose we take a pure sine wave. You can think of it is like a, if we sinusoid, it can be sine, cosine or combination. Let us say we are talking about a continuous time signal a equal to xt equal to a sine omega t, where omega here let us say we have taken 1 millisecond. That means we have chosen here some omega 1 is equal to 2 pi f1, where f1 here we have considered 1 kilohertz. Okay. So, we have considered 1 kilohertz is my frequency. Now, if we do power spectrum, that means this is a periodic signal, right. So, this is a periodic signal, and if we want to extract the frequency component of a periodic signal, then what we should do? We go for Fourier series, right, Fourier series. So, I am not going too much mathematics of that because these are well established and it is a different course, but I want to say if we apply Fourier series, then we want to get the power spectrum of this continuous signal, and it will be simply a single frequency component. And here I can say Fm equal to F1 because this is my injected frequency and sometimes it is called modulating frequency. So, in the frequency spectrum, what is y axis? Y axis is the power spectrum, power spectral density, PhD. It is called power spectra density. In short form, we write PSD. How does it look like? So, power spectral density, if we write the Fourier, that means if x, in this case it is V s of t, if we pass through, okay. So, suppose V s of t, if we pass through like a sampler block, sorry, here we are talking about power spectrum. So, we are not talking about any sampling. Suppose for this signal, if we apply Fourier series, then what we will get? We will get something like a x of k. What is x of k? X of k is the Fourier series of the Vs of t, where k implies it is basically the modulating here the instantaneous frequency. That means, if I take this is my frequency axis. So, k corresponds to, so k f divided by your modulating frequency or basically the periodic frequency, the time, that means your it is like it has switching frequency is fixed. So, sorry, your periodic frequency is fixed. So, periodic frequency, right, and here you will get f by fm, that means 1, because it has only one frequency component, that is a fundamental. Now, if we talk about, let us say, other than sine wave, suppose we talk about a triangular wave like any arbitrary shape, then we will have time period t, this is my, you can say, modulating period, and my Fm will be 1 by Tm. But in this case, if you apply Fourier series, because it is a periodic signal, you will get harmonic content other than, that means k will be 1, 2, 3 and so on, you will get power spectrum. And since it does not satisfy any symmetric property, so you will get even odd all type of harmonics. And if we take the for this x of k, if we take x of k, that its power, basically you will find the Fourier coefficient, that means so we want to see what is the power content, because we can apply Parseval's theorem and find out what is the power content here. in this signal, that means in the Fourier domain, then you will find the power spectral density. Now, we have talked about a periodic signal. Suppose this periodic signal is passed through an A to D converter, an ADC, followed by a D to A converter. That means, first we are discretizing the signal, that means we are converting from analog to digital, and then we are converting from digital to analog. If the sampling rate is very high, and as we know from our common sense, then the output signal, this is like your, you can say Vs dash t, because this n should be here, because it is a time domain, it should be time domain, because it is again analog signal, continuous time signal. So, Vs dash t, which is the output of the ADC followed by DAC, this will be almost equal to Vst if the sampling time is very small, it is very small and the quantization resolution is very high. That means, you have a very higher order number of bit, then they are almost like a same signal will be represented. But in reality, neither we have very excessively large number of, you will get number of bit, nor you will can find out, or you cannot, you can apply a very high sampling rate. So, there should be some limit. So, here we are talking about the sampling of this signal 5 times of the periodicity. That means, we can think of the blue signal, it has FSW is the time period, sorry, frequency, that is the frequency of the analog signal, and we have sampled the signal which is shown here by the red one. This one is my sample signal after sampling, and what is sampling rate? Here 5 times. So, you will see there will be 0 order hold effect, right. So, the sample signal will not look like exactly like a sine wave. So, there should be distortion in the waveform, and if we take even higher sampling rate, then you will get somewhat close approximation of the actual digital signal, right. But here we have not considered any quantizer. If we apply quantizer, you may even get somewhat more distorted waveform, but for the time being we are only talking about sampling rate. So, if we increase to 10 times, then we will get more closer behavior of the analog signal, but still they are not exactly same. So, now the question is, what should be the sampling rate? Should we go to 100 times? Should we go to 200 times? So, it is simply impractical, because we are going to apply such sampling in our switching converter, in which the switching converter itself is running at a higher switching frequency. So, we have little flexibility to increase the sampling rate, like we cannot impractically increase it, right, very high sampling rate we cannot say. A practical signal, even if you want to sense a periodic signal, our sensor can, even if there is no, even if we take negligible variation in the time period, it can so happen the sensor can have some uncertainty. The distortion in the sensor can also add up this kind of variation. Okay? So, as a result, after sensing the signal, we will get something like band limited signal. So, if it is my frequency spectrum, and if I take this is my nominal frequency, my modulating frequency. So, in perfect case you should have got like this, only a single frequency component, but in reality you will get something like this, something like this. That means it is band limited. So, we will take certain band, we are not probably going to take too much of band. So, it is a band limited signal, and we are talking about the power spectral density. Since we are talking about a real system taking into account all type of uncertainty, so we will talk about a band limited signal. Okay? So, certain band, even if we have a very high frequency component in the actual signal, our sensor will have a bandwidth. So, we will get some sort of band limited signal, and if such band limited signal, if we take this sine wave, pure sine wave to be a band limited signal, so we will get the power spectral density of the analog signal looks like this, something like this. Now, so this is the power spectrum of the band limited signal that we have discussed, where this signal is the band limited is power spectral density. And this is, I told you that if we take a even switching converter, what we consider generally, we have a sensor, feedback sensor, and the feedback signal will also have some band. Okay. So, this band limited signal, if we take the power spectral density, this is it looks like this. Assuming in normalization the power spectral density is 1, the peak value is 1. Okay. Now, we want to see what will happen in the power spectral density of the sample followed by like ADC followed by DAC. That means, again it is a continuous signal, it should be Vs dash t, because this will come actually here, because it is a discretized, and then after that it will again become a continuous time signal. Now, how does the sampling rate affect the power spectrum of the sample signal? So, this can be proved mathematically if you take the power spectral density of the sample signal. I am talking about Vs dash, that means it is passing through ADC followed by DAC. It can be shown that it is 1 by Ts, and which is the sampling time period. So, here Ts is the sampling period. It is a sampling period. It can be shown 1 by Ts sum of this, that means you will get a train of kind of spectrum, right. So, that means in the power spectral density you will get a sum of multiple things. How does it look like? So, it will look like the band limited signal that we have considered, which is in the continuous time signal or the analog signal, that is scaled by 1 by Ts, because we took earlier it was 1, that was for the actual band limited signal it was 1, but is scaled by 1 by Ts, and it will create multiple lobe. That means, one at the frequency of excitation, because this is a modulation frequency, that is the periodic frequency of the or the nominal frequency of the analog signal, and then on top of that you will get Fm plus Fs, then you will get another Fm plus twice Fs, Fm plus 3 Fs, and so on. And similarly, left side will get Fm minus Fs and so on. So, you will get side lobe, and all this component will have equal amplitude like 1 by Ts, and depending upon, now if we decrease this Ts, that means if the sampling rate is increased, this spectrum, that means the distance between these two spectrum will keep on increasing. So, as if then your another band actually it will repeat after very long time. Okay? And then it can be shown that at Ts tends to 0, this signal will asymptotically look like this signal. That means, as if they will again become like a analog signal if Ts tends to 0, and this comes this, because this theorem was Nyquist theorem, right, the Shannon sampling theorem, from where we can get the spectrum of this sample signal. Okay. So, now why we are studying this? Because in our switching converter we need to decide the sampling rate. Now, going back to the analog to digital converter, in our DC-DC converter we have output voltage. In fact, this is our sense voltage, where we can consider the gain of the sensor, but let us, for the simplicity, let us assume it is the output voltage, and we need to sense the output voltage. Remember, once you send a, this is my comment of the sampling comment, this is my sampling comments. So, these are my sampling comment, sampling edges, clock, I will say sampling clock edges. That means, whenever these edges come, it it gives the instruction to the ADC that you now sample it. So, this is a moment when the ADC will sample, but the moment you are instructing the ADC to sample, the actual data which will be available, that means the digital data, that will take time, because you have some finite delay of the ADC, the conversion time. But we still have not considered the delay due to the other part like a controller, other loop delay. Here we are only talking about the delay due to the A to D converter. So, that means even if we are sending the comment signal here and it is k minus 1, the actual data will be ready after some delay. That means it is ready here. So, from this point onward your data will be ready, this point onward. That means we need to take into account this delay, and this delay can vary depending upon what type of ADC you are talking about, what is the sampling rate of the ADC. And there are various type of ADC, like you can have a successive approximation type ADC, you can have pipeline ADC, you can have flash ADC. The flash ADC may be have a least delay, but it is generally not preferred because it requires impractically large number of comparator. Okay. So, there are like, or you can have serial ADC, parallel ADC. So, there are different type of ADC architecture I am not going to discuss, but the conversion time can vary from ADC to ADC, and there are different way of getting the digital signal. But we are concerned about the delay, even though ADC can sample, because there are two terms that comes into picture in ADC. One is called throughput. This is the rate at which ADC samples, right. That means whether you want to sample 50 mega sample per cycle, 10 mega sample per cycle. So, this rate will be decided by throughput. This is important, but more important for this power converter is the propagation delay. Or sometime in ADC terminology it is called latency. So, you call it as a latency. So, for us this is the one of the most important. This latency will decide what is my delay. So, if we take pipeline ADC, the pipeline ADC, the delay is generally decided by the number of stages, pipeline stages. So, if there are 6 number of pipeline stages, so your delay will be 6 times of the sampling clock. So, if you want to reduce this delay, you have to sample at a very high rate, and you have to check whether such sampling can be supported by this thing or not. Okay. So, the latency is the one which is very important for us, which decide the delay. So, now few things you have to keep in mind in order to preserve periodicity, because we should not abruptly sample, even though we sample once per cycle or 10 per cycle, but there should be some uniformity, some synchronism, because in order to preserve periodicity, generally the sampling rate is the integral multiple of switching frequency. If they are fraction, that means the sampling rate, if you take, let us say, the sampling rate divided by the switching frequency. Okay. So, let us consider a scenario. If you take something like sampling frequency by switching frequency, it is something like a n by m. That means this is a ratio of 2 rational number, 2 real number, 2 integer or 2 rational number. I mean sorry, it is a rational number, the ratio of 2 integer. Now, we generally take n is k times m. If k is integer is fine, but suppose we take k fraction, then what will happen? This will introduce some nonlinear behavior, and which can lead to quasi periodic behavior, sometime mode locking behavior. So, unnecessarily it may generate some sort of nonlinear behavior, which sometimes we call like a limit cycle, or it can be chaotic behavior. So, we generally avoid such kind of fractional sampling rate, or basically it should be integer multiple. And PWM clock and the sampling clock, they are generally synchronized, sync. And third, the sampling frequency either can be integral multiple of the switching frequency, it can be higher or it should be lower, but we should not take generally the lesser number of sampling rate. In fact, that may be possible if the converter is running perfectly under steady state. Then in order to save power or avoid computation, more and more computation, in fact you can keep your processor idle and you can just continue with the value which is already stored, a fixed number, because ultimately the digital control under steady state, it will look like a open loop. That means your error voltage in digitally becomes 0, and then there will be no update in the digital controller. So, it will look like a constant number. Okay. So, in that case we can even reduce the sampling rate. Okay. So, there are many architecture or many kind of intellectual properties as well as research papers are available, but I am not going to discuss. Generally we are talking about, for sake of analysis, it should be equal to this. Now, the sampling frequency same as switching frequency is a scenario. Suppose this is my complete waveform, if this is my output voltage ripple, and you can see the output voltage ripple looks like somewhat dominated by the ESR ripple, as if it is capturing like a similar nature of the inductor current. So, we have, this is my average output voltage, and the actual output voltage will also have a ripple. Now, if we take one sample here, all these sampling point, so here we are sampling here, as if we are sampling at this every edges, this is the sample waveform. Then what will happen? Actual power spectrum of the analog signal, that means if we take the power spectrum of this analog, like means analog voltage, then we know the output voltage in a DC-DC converter should behave DC, right? That means ideally, or if this is my time domain waveform, so our output voltage, if we take in division like a 1 volt or 2 volt in oscilloscope, we will simply see it is like a flat output voltage. But if you take AC couple, that means if you take zoom this part, AC couple mode, if you go to AC couple mode, then you will find this kind of ripples are there, and generally these ripples are kind of around 2% of the steady state value. So, you can imagine that the power contained in the AC couple signals are much less compared to what is there in the DC couple, which primarily dominated by the average voltage or the DC voltage. Okay. So, you will get a high peak at 0 component, then Fs, which is our switching frequency, that means this you can say the fundamental component, this is my fundamental component corresponding to switching frequency component. Then we will get harmonic, and as we move higher and higher harmonics, the power content will get reduced, because the maximum power will stay in the DC component. Now, if we take one sample per cycle, then what we can expect? We saw. So, we saw that one sample, that means your sampling frequency is same as switching frequency, and we know that here at 0 frequency it will also have a side lobe which is here, that means we will get FSW, then we saw FSW plus sampling frequency, and in this case sampling frequency is same as switching frequency. So, we will get 0 FSW, 2 FSW, 3 FSW, and all will have equal amplitude, because this is a band limited signal. And we saw that if a periodic signal, if we take only this part of component is passed through a sampling block, only this part will be repeated multiple times, and they will be scaled, right. So, it will be 1 by TSW, they will be scaled if this quantity is 1, right, that we have seen. But now, since our sampling rate is same as switching frequency, for the digital controller we can only see up to Nyquist sampling rate, which is half of the sampling rate. That means, in the digital controller nothing will come beyond this, only component will come left side of this. So, as a result you will see only this part will come into picture. So, that means, but suppose if you take a higher sampling rate, then it may so happen in the Nyquist sampling rate you will get additional component, and that can cause aliasing effect. And so to avoid this aliasing effect, one sample per cycle is considered to be, in terms of power spectrum point of view, is very good, and you can get more detail in this book, and there are multiple papers of that. But only thing we can miss is that due to this reduction in the spectral peak, you may lose, because you can imagine you are only taking the bottom value of the sample, and if you take the average out, they are somewhat smaller than the actual average voltage. So, as a result, your sample voltage is here and actual average voltage of the DC converter here. So, you lose some regulation point, and that you have to anticipate by suitably providing an offset to the reference voltage, so that that can be taken care. Now, if you go to digital controller, so we discuss about one A to D converter, and we discuss this sampling rate to be roughly we are taking same as the switching frequency, right. And then after this sense voltage comes inside, it is the digitized one, that means it is both sample as well as quantized, and then it is compared to the reference voltage and we get an error voltage, and then it goes to the compensator. And then this compensator output, if we talk about sawtooth waveform in analog, or we can also consider the whole thing in digital. So, then in fact, this can be current also, that means here this provision is kept to show current, but in voltage mode control this whole thing can be digital and you may not need any DAC if you generate this sawtooth in the digital waveform. But in some cases people prefer to use this sawtooth waveform outside, because there are certain restriction due to the sawtooth which will impose a constant in the duty ratio, because this will be responsible for the resolution of the duty ratio. So, in order to improve the resolution, sometime some designer also consider D2A, but again you have to pay price for the D2A converter. So, in general most of the digital controller will be discussing, that means we are taking everything in the digital loop once it goes into the digital controller, nothing is analog after this. But once we go to current mode control, we will see this D2A converter can be also used when you want to keep the fast changing current loop in the analog domain. So, now output voltage sampling we have discussed this aspect. Now, suppose we want to implement a PID controller, that we discuss. So, if you want to implement a PID controller, we know in continuous time we know that a PID controller, that means G of S is generally Kp plus Ki by S plus Kds by tau ds plus 1, and this is my digital derivative filter. Now, in case of digital, this is like a proportional control, the error voltage is coming, because as if there is an error voltage and after the error voltage we put a PID controller. In case of analog, simply Kp. Now, in case of integrator, that means if I take the time domain, that means it is simply Ki is outside integrator error voltage times that integrating over, you can start from 0 time and you move on, right. Assuming that at 0 time there was no initial condition, or even if there is initial condition, that can be taken care. So, this quantity in digital control, this sum block can be realized using something called velocity algorithm or incremental thing, because otherwise if you simply, so this block can be approximated like a summing block, because the integration will become a summation when you move from continuous time to discrete time, and this can be realized by means of an incremental algorithm. For example, here you see, here it is UK. Suppose let us say we have represented, for example, let us consider we are talking about, suppose you want to get the u of, let us say u of I integral action is nothing but our analog gain VE into dt, okay, 0 to t, let us say. Okay. Now, if we take this 0 to t, that means if we take the, if we draw the error voltage, suppose we have certain this kind of error voltage profile, this is the profile of the error voltage. Okay? This is time. Now, we are talking about different sample, like we are sampling here, we are sampling here. So, only we have these available samples are there, we do not have full access here. So, these are the okay. So, let us say we have here, we have here. So, when you say integration, that means it is basically, suppose we are talking about this particular time, you choose some, let us say, to make it much more simpler. I want to highlight some part, that means let us say this is the part I am highlighting, I am highlighting some particular plot. Again you can put. So, in this part I am taking, this is the sample, again it is going like this. So, this is my t equal to, let us say, k t, and this is my t equal to k plus 1 t. So, here if we take the integration, that means let us say u I of some dash, where we are trying to integrate k I between k t to k plus 1 t v error t dt. Since this period is t, this period is t, so this area under the curve can be computed in different way. So, if you take this one, then this will be the area. If you take this one, this will be the area. So, based on that there are, or you can take their average, where this will be the area. Okay. So, this thing can lead to called forward difference formula, backward difference formula, and another is called bilinear transformation or Trustin method. So, I am not going into this, but this can be realized, this integral u of k, if we take the backward difference formula, u of k can be realized by u of k minus 1 plus, this is a discrete time integral gain into error voltage, where u of k minus 1, where k I d is simply continuous time integral gain into the sampling time. Okay. So, this can be represented by this. So, this is a velocity algorithm by which, and the derivative, if we take dv0 dt, so here it is taken as v0 k minus v0 k minus 1 divided by t. So, this is what it is taken, and this whole thing into k d is my this. Okay. Now, coming back to our digital controller, as I said, this is A to D converter, your sample voltage, this is error voltage, then control voltage, and now this sawtooth waveform is generated inside the digital controller. So, there is nothing outside. Okay. And we have this, if we want to draw the waveform, and we have discussed, generally we need to send the sampling command much earlier, because it will take some time to convert the continuous time signal, like it will include the ADC conversion time and controller computation time, and this time can be pretty large. In fact, it can be comparable with the switching period, or even some cases it can be higher also, because we need, at high frequency we need to reduce the burden of the computational burden. Okay. And now we are going to have this sawtooth waveform, and this is our sampling clock, and this is actual switching. So, here as if once you get the sampling data, this data will be computed and will be ready at this point, because as if this error signal will go through our PID controller, and output of the PID controller will be ready here. So, it will take care of the ADC conversion time plus the PID controller computation time. then we can do regular PWM operation. If we go to analog current mode control we have two loop control. One is the current loop and the other is the voltage loop, right? And we know the current loop, voltage loop can be sampled once per cycle, but the current loop cannot be like that, because the current ripples are quite large, and current ripples are generally, we have discussed in the beginning, like in our lecture number 7, that it is taken to be around 20 to 30% of IL average nominal value, okay, and that is why it is pretty large, whereas for output voltage ripple it is 2% of the nominal voltage. So, where we can take one sample per cycle for voltage, it can retain more or less the information, but in current we cannot do that. So, the next question, how do you digitize the peak current mode control? Should you digitize the voltage loop, should you digitize the current loop, or should you digitize both the loop? So, one of the solution, if we go for mixed signal, that means since our current loop require faster, it is a fast dynamics and we need to retain the ripple information, we should not now digitize the current loop. So, current loop, let it be in analog domain, but the voltage loop is digital domain. What is the advantage? Because since you have a compensator in the voltage loop, so we can play with the tuning that we have learned, right? Because we have already talked about gain scheduling, different type of control algorithm, where you need to adjust the controller gain based on the operating point requirement. We have also learned the large signal tuning, where we need to update the gain based on the operating condition. So, that can be easily done in the digital controller, and then the reference current will go, it pass through a D2A converter, and then the reference current. So, here you can think of it is my reference current, peak current, and that is compared with the inductor current in the analog domain, and that means we have an analog comparator, and then the comparator output is digital. So, then we can put a latch circuit, the whole dead time, and this whole dead time everything is in digital. So, we can adjust the dead time based on our load information and other information, right. So, here the first current dynamics is present, it is in analog domain, high performance control can be implemented, and I will show you some case study in the future lecture. Adaptive ramp compensation is very easily possible, because ramp is in the digital domain, but you need an extra A to D2A converter here, and high bandwidth analog comparator is still required, because that consumes a lot of power. And so, our next target is how to replace. If we take the mixed signal current waveform in a boost converter, as I said, we take the output voltage sample here and we provide this delay time, so that our computation of the controller, that means this whole process can be completed, this delay, that means here it is a TS delay. This whole process of sampling as well as computation can be completed, including the DAC, it includes the DAC, so that your analog reference current is ready. Once it is ready, then your actual switching clock starts. So, this is a switching clock start. Then switch turns on. Now, it is a regular trailing edge modulation, that means it is a regular trailing edge PWM, but with some sampling delay, and since we are taking the sample during the off time, that means when the switch is off. So, this is sometimes called interval 2 sampling. Interval 2 sampling. Okay. So, once you, that means we can realize this mixed signal current mode control implementation. So, you can see everything looks like our analog control what you learned, there is nothing new. Only thing, due to the sampling, there has to be some delay. Another interesting point, in analog current mode control, the peak current is coming from the analog loop, where the peak current actually varies within the switching period, because it is a continuous function. But in digital control, since you are sampling once per cycle, this peak currents remain constant for the whole cycle. So, it looks like a constant current reference for the whole cycle, and it will get updated in every cycle. In case of fully digital, we know that now the current loop is in digital domain, but we need to sample either at a high sampling rate, or we can sample, that means cascaded loop. Either we can use a higher sampling rate, that means this n, n can be very high, but that is called multi-sample, but generally that will consume lot of power because a ADC sampling requirement is very high. Or you can sample the same rate of the ADC of the voltage and then you can add a ramp. For example, if I draw a current like this is my inductor current, right. Now, I want to take this sample. Now, in the digital controller, I can add a sawtooth waveform inside. It is like a STR case, like I can emulate. And but the question is that what should be the slope of the, this is like a compensating ramp sort of inside the digital controller, but this is actual current slope. So, how can we get the slope equal to this current slope? It is not in fact required, okay. And there are many architectures, many techniques are available where either you can find alternative way, and there are many such things. So, but we are not going to discuss here. Only thing, we need to get the right slope. It need not to be the exactly equal to m1, but it also has some stability requirement, and that I am not going to discuss here. But the bottom line is this: we can emulate this current. How does the waveform look like? So, if we take the sample of the current, because since you are taking the valley current sample and you need to emulate this, but as I said, when you send the sample comment, generally it takes time to get the actual sample available because there will be A to D conversion delay. So, generally we cannot take the same sample and emulate in the same cycle. So, what is the common thumb rule? You take the sample of the current of this inductor current in this cycle, but you emulate in the next cycle. That means, this valley current as it is extended here, now you are adding this ramp, and this, the black color is the ramp that we are adding. That means, if I use a red color, so this is the ramp we are adding here. So, this similarly this current is extended here in a adding ramp here. So, by that way we can implement fully digital current mode control, and there are many literature, and in future we may come up with something like a reviewing all this architecture, but for the time being there are different type of architectures are available and they have various stability property requirement, and those are fundamentally different from analog current mode control. Like the current loop stability can be requirement is much more stringent, or basically more ramp slope. That means, you need MC to be higher than M1, and how much higher, and there are many architecture where you can also manage MC equal to M1, but we are not going to discuss here, but I think it is possible. But if we go to variable frequency control, we have talked about hysteresis control, right, and we talked that if we use a hysteresis current band, then we can keep the current ripple within the band, right. So, here again the current inductor current is analog domain, and the reference current is coming, which is a 2 reference current is coming from the digital loop, right. So, this hysteresis band, either you can implement a hysteresis comparator, or you can use, there are architecture that I will discuss shortly, that you can use a single comparator and single D2A converter. So, you need a D2A converter here. So, this will come output of D2A converter, and this D2A converter input is nothing but the controller output. And here if we sample once per switching cycle, and it is reported in this paper, the one sample per cycle, then you can perfectly stabilize this whole hysteresis control using one sample per cycle. But since the hysteresis control is a variable frequency control, so we should not use a uniform clock, and that is well reported here, because if you use a uniform sampling clock, it will lead to multi-limit cycle oscillation. And what we have to do, we have to use a event based sampling. That means, the event is here, whenever switch tries to turns on, then you take the sample, okay, and then you provide some delay where the switch will turn off after certain delay, and then you continue, okay. So, by that way you can ensure that the peak reference current will not vary throughout the whole cycle, and that will make the whole system. That means, in analog hysteresis control we saw the actual current ripple is smaller than the hysteresis band because of sensitivity due to the gain, controller gain. I think in lecture number, I think it was in 4th week, I believe, or 3rd week, I think it is where we have discussed about in detail about hysteresis control. I think it is in 4th week, where we saw for analog hysteresis control, your hysteresis band is higher than the analog inductor current ripple. So, but here by means of one sample per cycle you can make them equal, okay, and you can make it stable. And if you go to variable frequency constant on time control, in fact, in the next lecture we will show the waveform, the experimental result that it remains same. And if you go to constant on time control, it is also variable frequency control, we have learned. Again we can use this event based algorithm. For constant on time, we generally take the sample before switch turns off, because that means this on time actually comes from our monoshot timer. So, once the timer almost finishes the timing, then you can send a sampling command, and then after short time you actually turn off the switch. Then that sample actually take the valley current generate, and then you can do the regular valley current operation. So, in the sense that the valley current remains fixed for the whole duration, and again it is a event based sampling, one sample per cycle, and you can stabilize and you can get wide operating range. And this is also reported in this paper, where you can stabilize, and we have shown that by means of one sample per cycle we can get a stable periodic behavior for a wide range of operation. And since in variable frequency control we saw the current loop never become unstable for the entire duty ratio range. So, you can take the benefit of that current loop inherent stability as well as the digital controller tuning, where you can adjust this time period can be adjusted by setting a suitable on time. That means, we can set the suitable on time in such a way so that we can regulate the switching frequency. So, we can also implement the peak current mode control for constant off time, and that we can discuss in the next lecture, where we can actually implement the peak current mode control variable frequency modulation. So, in summary, we have discussed fixed frequency digital current mode voltage mode control, fixed frequency digital current mode control, then variable frequency digital current mode control, and event based sampling in variable frequency control for hysteresis as well as constant on time modulation, and it can achieve, we will show in the next lecture, wide like a stability range for a wide range of operation. So, with this I want to finish it here. Thank you very much.